over the fundamentals of fuzzy logic we've covered already, to make sure we've got the basics right, and then from there we'll look at the example. Okay, so we'll go over all this a basic introductory part on fuzzy logic, where we discuss the very basis of fuzzy logic, stemming from the way we human beings deal with common situations. We don't tend to be very precise in the way we deal with problems we face. And for example, we've discussed in class examples of, for example, temperature. We say we are warm or it's cold or hot. We don't tend to use precise terms like temperatures 26.7 degrees and so on. Okay. Similarly, if you're dealing with any other parameters, for example, height, mass, or any other parameter you would tend to measure in engineering or in a scientific study, you will typically not go for this type of precise, crisp values. So this is basically what we've covered in class. We've compared quite lengthily the concept of binary logic, where you could be either in one class or the other. And you've seen, yes, it's fine. We've applied the concept of binary logic in electronics, and it's very useful to model discrete processes. But when it comes to, again, our real life situations, it's quite difficult to apply binary logic. For example, if, again, we've seen example of height. If you set a threshold for categorizing height as, for example, long or short, you can't set a clear-cut threshold. If you do that, it's not representative of how we deal as human beings. So this is all the concept of uncertainty and precision, which we've discussed in class. So now, stemming from binary logic, then Professor Zadig came forward with fuzzy logic, in a way, all the frameworks, operations, and how we define a fuzzy logic system. And this is what we have already seen in class, fuzzy logic in terms of the tools, the methods that we apply. And we've seen here, we don't have this sort of abrupt change from one class to the other, but rather we have a continuum. So we've seen that clearly. This example. So these are all the framework we're setting, mathematical frameworks. So this is how currently you have a sharp change. Yeah, from if, for example, you're defining a class here, which is just taking a step up, and then as you go before a threshold, of that threshold, you are suddenly changing classes. So that's not very, very useful for us. Yep. So if, for example, we use a set membership in this way, here we can see some more gradual change and more representative. So when we use this type of membership set, then we're talking about membership value or degree of membership of an element in a given fuzzy set. Yeah. So one example we've taken in class is, for example, if you're defining an ellipse with the minor and major axes, and you give the length of major and minor axes. So as you take the ratio A over B here, when A over B is equal to 1, it's a perfect cycle. But as you start moving away from this threshold, you start getting less of a cycle, if you want. So you have a mathematical equation given there, a mathematical equation given here. So if you plot that, you get something in this way. So you can see here, 1 would be a perfect cycle. So membership is 1. But as you move away from it, it means as you're moving here on the left or the right, you're actually coming like an ellipse. Yeah, you're either elongating the along the vertical direction, or you're elongating along the horizontal direction, and so you're having less of a cycle. Ultimately, in this case, we're saying when A over B exceeds 2 or 5, then we are deviating on the cycle. But for example, here, if you find any point here, we take an example, and A over B is 1.5, we are saying this geometry would have a membership around 0.45 in the circle membership set. That's what we're saying. I hope this is clear. We have discussed at length. This example was taken in class and discussed a bit. It was last experience supposed to differentiate what is actually probability and fuzziness. We've seen this very different. I hope this also is very clear. Now, when we do classical sets, which we've studied in primary school, when we use Venn diagrams, so it had a very clear boundary, crisp set boundary. But when we start using fuzzy sets, this boundary becomes more blurred. Okay, so some definitions we've seen: the universal discourse, X is everything that you can have in the set, just like typical we've been using with classical sets. This again discussing this thing of crisp value or a continuum of membership. Then you have the cardinal number is another thing which we might come across. Yep, we discussed that in class. And then typical operations like is a member of, is not a member of, is subset of, or is not a subset of, that's fine. And then also another thing is the power set for all possible combinations, but the null set is very important for us. Yep. So using the null set now, we can talk about negation. We'll see later. Now, when we talk of sets, we know that we can do union of sets, we can do intersection of sets. As we've learned in primary school, we can do complement of sets. This is still in the sphere of binary sets, classical sets. And then we see how we actually extrapolate this to fuzzy set. Now, we also have a difference operator, which is sort of A minus B. Okay, so we've done that in class, how we represent these four operations: union, intersection, complement, and difference one. We've concluded we can actually implement the difference operation by taking A intersection the complement of B. Now, some further properties of classical sets, so commutativity, associativity, distributivity, idempotency. So we've seen that, identity. Important for us to grasp the meaning of these and not just learn by heart, like we've discussed in class. Transitivity, involution. So two special properties which we've learned in the field of digital electronics, which are of course applicable to classical sets, De Morgan's laws, yes, and also something called the excluded middle axioms. So they are as follows: if you take a union of A, which is complement, you get the reverse, and if you take A intersect, which is complement, you get null. So it means there's nothing in common. And De Morgan's principle, we've studied that in digital electronics. So the complement of A intersection B is a union of the complements. And the other equation, the other law, is the complement of the union of A and B is intersection of the complements. So the depiction of De Morgan's principle using Venn diagrams have been done. Yep. So we've done that in class. And in general form, write the general form of De Morgan's principles for n sets. So we can extend that, of course, to n sets. If you have A intersection B intersection C, all complement is still going to be the union of the complements, and similarly for the second equation. Now, what we're doing here, as example we've done in class, is taking some discrete sets for A, B, and X, again, like we've done with classical Venn diagrams, and then write memberships for A and B, and then start doing some operations. So we've done that in class using the notation. We'll see that in the slide further down. And we have in this exercise, we've sort of set some rules which can be extended now to fuzzy sets. And we've done this example, and we'll see it later. So this is the notation we're going to use to represent an element in A and its membership value. So x1, x2, x3, xn would be instances or members found in A, and the numerators are simply the membership values. So if you talk of classical sets, the membership values would be either 0 or 1. Yep. So going back a few slides, this exercise we've done here with the sets A and B in classical sets, we've found, I won't say discovered, but we've inferred from the examples we've done is reduce that if you want to do union, it's a maximum of membership values, and intersection is nothing but a minimum of the two membership values, and of course when you complement it's 1 minus. So this is why we're coming with maximum, minimum, and the 1 minus operations is very simple. It's because this is extendable to fuzzy sets where we'll be dealing with not just 0 and 1, but it will be a continuum. So again, we've discussed that length in class. So now coming to fuzzy sets, so we'll discuss this notation for representing fuzzy sets in discrete times. If you want to depict it, of course, as a graph, you can do it. But if you want to do it in discrete, then do it as well. So we've done this exercise as well. How do we show that De Morgan's principles hold for fuzzy sets? So we've seen, yes, they do hold. So we've done this part here on a graph, and this one as well, we found a match, and this one as well. So they do actually hold. Now, what about the axiom of excluded middle and the axiom of contradiction? We've seen that they actually do not hold for fuzzy sets, but they do, of course, hold for classical sets. Yep. So we've done these examples as well based on the operations we found now for carrying out complement, for carrying out a union, intersection, or subtraction. So we are able to do all this from simple examples like that. Discrete terms using notation we've already set for fuzzy sets. Yeah, we established these sort of notation, but at the same time, of course, if you had to do similar operations on membership sets, on graphs, you could do that as well. Yep, so we have covered this in class. If there's any doubt, you can email me about it. We can discuss in a subsequent session. Okay. Now, this is another way you could show the Morgan's principles actually hold, is actually to use this type of notation and to carry out. So if you just take a random set like A, B, and then you do find the terms for the De Morgan's law on both sides. So you find this one, and then you find this one, and then if you answer the same things, it's actually holding. So we've cross-checked that. Now, coming to application of fuzzy logic for engineering applications. This was sort of a second part of this lecture series 5, and we've discussed in class, but I would want to do a recap again here to make sure we're on the same wavelength. This was the a topic we discussed before actually went. So we've seen if you want to design a fuzzy logic system, you're going to have 4 main components. Then you have a fuzzifier, so that you can convert your crisp values into fuzzy sets, and you would typically do that by the membership sets. Now, the rule sets are the knowledge base, if you want, or the formulation, the rules, typically if else. It would of course have and, if, and other kind of operations that allow you to combine your input to create your output. And always a relationship between your input and your output. Now, when you apply the membership set and your rule set, then you are using the inference engine, you would get at this point a fuzzified output. Because your input are fuzzy sets. When you apply fuzzy operations, fuzzy sets, you get a fuzzy output. So at this point, when you inference engine and you apply all the previous steps, you can get fuzzy output. So you would have to defuzzify because a fuzzified output is not very useful for a system. A discrete control system would not be operating with a fuzzified output. So we've discussed the defuzzification step as well. So I think this is all okay. So we know we're going to get real world crisp values, which we have now to feed to our FLS, and from there carry out all the steps we've said. Yeah. So example we've taken here is for temperature. So if you want to have an input variable called temperature, you would have to define linguistic variables first, and these variables would have values. For example, if you have a fuzzy linguistic variable temperature, its possible values could be cold, warm, and hot, as we perceive. In the real world, like I said, we will not be dealing with crisp values as such human beings, so we want to translate that crisp value into these values. This is linguistic values. So here I've put cold, warm, and hot, but of course you would have other values. You would have mild, cold, or very hot, for example. And once you have set these values, you will have to map these values for one linguistic variable, temperature. These are the, if you want, the delineations, the way you define what is cold, what is warm, what is hot, again, without any sharp transitions. You want the memberships to be on a continuum. Here we're using, of course, triangles without linear type of function, so that it's quite easy to manipulate mathematically. There's no reason why you can't use other types of functions like Gaussian, like sines, and the previous case exponential. We've seen with the case of the ellipse, where we had the minor major axis. So this was not really linear. So you could other types of functions as well. In this case here, and to illustrate the example, we're going to use linear. Okay, so important for us now is once you define the membership functions, if I give any crisp value in terms of temperature to you, for example, here I'm asking if I give a temperature of 20 degrees Celsius, you could work out the membership value in cold, warm, and hot. So we've done that. Yep, and I think there was a small mistake here. We've said actually it's I just correct that immediately. We found to be 0.4. I've corrected it in the remainder of slides. I'm just making this small change here. Yep, so this one we've said it would be 0.4. Right, actually this one here will be 0.33 as we see late. Okay, so let's go back. Yep. So I'm going to change the remainder of slides, but I omitted this one. So if I give a temperature of 22 degrees to you, and you're asked now to find the membership value in this free sets, in this free fuzzy set, so in the free values of your temperature input, links variable, warm, cold, and hot. Yeah, you can do that. So this is what's showing here. So 22 degrees Celsius is going to have a value of 0.4 in warm. It's going to have a value of 0.2 in cold, and would have a value of 0 in hot. This is how it is. Now, another, if for example, if you take another value, 27 degrees Celsius, so you'll find it has a value of 0.133 membership value in the hot glass. It would have a value, a membership value of 0.6 in the warm glass, and it would have a value of 0 because after 27 cold is in this way. Given temperature of 27 degrees Celsius, you could work out the membership values in these free values of your linguistic input variable temperature. So this is fundamental. You should be able to understand how you actually take crisp values and actually falsify it. So the falsification is done using membership functions. Okay. Now, once you do that, to generate an output based on inputs, a knowledge base is required, which is typically represented as an if-else rules, but we'll see, of course, it could be represented as a fuzzy matrix. And once you do that, then you can apply your knowledge base to get your fuzzy output. Yeah, this conversion of fuzzy set, the crisp values known as defuzzification, which is essentially the last step. So we've illustrated this whole steps from fuzzification, membership settings, a rule set, inference engine, and defuzzification using an example here. So of an air conditioner system, which have a target temperature which you want to achieve in the room, and then of course you have an actual temperature which is prevailing in the room, and then the output is going to be free here. It's going to be either you cool the room, or you heat the room, or you don't do anything. Yeah, so these are the steps that comes out of the 4 main blocks we've seen for the physics system. In this case, like we've done earlier, the input temperature would have 3 values. Yep, so cold, warm, hot. We're going to use the same membership functions we've seen earlier, so triangles and linear functions. The output command says heat, no change, or cool. So next step now, once you define your values, you'll have to set membership functions. So the ones for temperature we've seen earlier. So we've drawn that already. Now, the membership function for the output, like we see in class, can be set arbitrarily. It's up to you to understand what they mean. It could be different. In this case here, we're saying basically if you get an output which is above 75, around 75, or from between 50 and 70 and 100%, is going to mean you have to cool. If it's around 50, it means you have to do no change. And if it is between 0 and 50, it means you have to heat. Of course, the further you are to left towards 0, it means more heat you have to provide. The further you're to right towards 100, it means the more cooling you have to provide. And the more central you are over 50, it means the least amount of heating or cooling you have to provide. And if exact at 50, it means you are very happy. Don't need any change, any cooling or heating on the system. Okay, so let's see how we actually solve this. So next step now, so we define our linguistic variables. We know what our output is. We are able to set membership functions for our input and outputs. Now we have to set fuzzy rules to be able to rate our output to input. So I'm discussing class. This is a very logical step. So this problem is not expert system design in a way. It is in a way, yes, I would agree, because we have a notion what you want to do here. If, for example, room temperature, if you look at the first condition here, if your room temperature was cold and the target temperature was warm, then definitely going to heat. So this is some logical common sense for us. But like we said in class, if you have a process, a problem which you don't actually know what the command would be, you would have to consult experts. In this case here, we're setting the rules here because we understand the concept of cooling and we can decide how a system should behave, but it's not always the case. Now, the second one we've seen, if room temperature is hot, so your room temperature is hot and you wanted it to be warm, then definitely you're going to cool. Now, if your room temperature was warm and the target temperature was also warm, then you will not do anything. So this is how it maps out now. Yep. So based on these 3 combinations we've seen, but in all you have 9. So if you construct a fuzzy matrix here, where the column here is your temperature, so prevailing temperature in your space, in your room, and so target means what you want. So you have 3, same for each one. So cold, warm, hot, and cold, warm, hot. Why? Because in this case, both are temperatures. So the values we have for temperature in general would be cold, warm, hot to be the target, or the prevailing temperature. We have the same. So if you have these 3 combinations for your actual temperature and the 3 combinations for your target temperature, you have 9 possibilities. This is where you get the first in the action to be taken. Yeah. So we discussed that. For example, if your prevailing temperature was cold and target is cold, it's going to be no change. If your prevailing temperature was warm and target was cold, you wanted cold, it's warm. So you cool, same comment here, cool, and so on. So if we look at all these possibilities, this is what we're going to come up with. So let's see here, we're able to relate through this rule set. It could be, of course, translated into if-else statement or the fuzzy matrix we're seeing here, but principally we're able to relate our inputs to our output. Once you're able to do that means, for now, a given temperature prevailing in the room and a given target temperature we want to achieve, you can find the values in these 3 classes, and you can compute the output. Of course, will be specified form for no change, and no change here will be an output. So what would be output no change? We have 3 possibilities. Yep. So you're going to go for no change if your prevailing temperature was cold and target temperature was cold, or prevailing temperature was warm and the target was warm, or the prevailing temperature was hot and your target temperature was again hot. So this diagonal here is actually 3 combinations, which are conjunctions, and the possibilities. So either this one or this one or this one is your destruction. So similarly, if you want to work out an output heat, what is heat? So heat is going to be when prevailing temperature is actually cold and so it's a convection, target temperature is warm, or so destruction now when the prevailing temperature was cold and target temperature was hot, or third possibility is when your prevailing temperature was warm and your target temperature was heat. So was hot, sorry. So this is the expression you're getting for the output command heat. Similarly, you can create a rule if you want, or an expression as a disjunction of conjunctions. So 3 combinations again, 1, 2, 3, and they are alls. So if you're able to do that now, then you can compute the output command. So let's take an example here. So to analyze the fuzzy logic system operations, say the target temperature is 22 degrees Celsius and the room temperature is 27 degrees Celsius. So you want to get 22 degrees Celsius and the room temperature was going to be the room temperature is 27 degrees Celsius. Okay, so for target temperature of 22 degrees Celsius, you can work out your membership sets in cold, warm, and hot. Yep, so we know how to do that. We've done that earlier. So similarly now for a temperature of 27 degrees Celsius now, which is the prevailing room temperature, you can get your values in cold, warm, and hot. So as follows, and of course it follows from the present. So 22 degrees Celsius, you're getting 0.20 in the cold glass, and you're getting 0.4 in the warm glass. So at 27 degrees Celsius, which is the prevailing temperature, you're getting a membership value of 0.133 in the hot glass, and you're getting a value of 0.6 in the warm glass. And again, of course, at 27 degrees Celsius, your membership value in the cold glass is 0. And at a value of 22 degrees Celsius, your membership value in the hot glass is 0. So this is where these values come from. Yep, all these sets of values come from there. Now, next, of course, we evaluate the rule set. So it's an inference engine that we talk about. So based on the fuzzy matrix we set, you are able to evaluate the three outputs. So the example which is here is for no change. So we've seen that already. So if room temperature was cold and the target temperature is cold, you're going to go for no change. Or if room temperature is warm and target temperature is warm, or room temperature is hot and target temperature is hot. So we've seen earlier, of course, when you do ending, it's taking minimum, and when you do O-ring, it's taking maximum. This is why this operation here translates to minimum. So this one also is a minimum because it's ending, and this one also is a minimum, but overall you're taking O and O, so you take the maximum of the minimums. What you're getting. So finally, so we're getting the command no change has a membership value of 0.4. If you follow the same rule now and try to evaluate what would be the output, cool and heat, because of course we have three values for output linguistic variable. So this one we've done already, like a few slides back. Now if you want to find command heat, so again, you look at these combinations here. Okay, so you're going to have a membership for target warm and prevailing cold, and target hot, prevailing cold, or target hot and prevailing warm. So these are the command for this one. You have three minimums again, takes a maximum. So in this case, we're getting these values here. So these values have been pre-computed. We have seen them already. So if you plug in here, you get a command for heat of 0. Now, what about cool? Again, you have three combinations. One, you have three conjunctions, so they are minimums, and then you would take this junction, so you take the maximum all of them. So same for heat here, you're going to take here, for example, this particular combination here is going to be target cold and temperature, prevailing temperature warm. So this is one combination. So the other two combinations give these two minimums and take maximum of minimums. I see here. So we get a membership value in the command cool of 0.2. So once you are able to get the values for each, the membership values for each of the output value you have, then you can just map it onto the membership set as follows. So if I just go back here, we found no change with 0.4. So this is a 0.4 here, so no change, 0.4. For heat, we find it to be 0. This is why for heat, you don't find anything. It picks up, of course, when the no change starts taking value. And then we drop down to 0.2, which is cool now. So the membership cool here, it will drop down and go to 0.2. So we get an output, a falsified output. So this is the falsified output. But like we say, this is not very useful for us, and we would want to get a crisp value out of this. So basically, the physical system is like a black box. You're feeding in crisp values, and you want to get crisp values out of it to be able to control the process. Be it in this case, for example, if you're controlling an air conditioning system, you would want to get a crisp value to feed the controller. You can't feed a falsified output like this to feed the controller. So now we want to get one single value. So this defalsification step can be done in different ways. So I discussed in class, we have a central method. So if you want to be exact here, the central method is going to be integration of a product or membership with X, and then over the integration of a membership. So this one is an area. This one is a movement of an area if you want, but of course it's mathematically exact. But since we're talking about fuzzy set, we're already into the uncertain realm here. We can simplify the expression by taking summation. We know areas or moments can be approximated as summation, the trapezium rule being one example. So here in the denominator here, you could take a sum of your membership, and the numerator you could take a sum of product of your membership and the value itself. Yeah. So this is one method. There are other methods which have been reported in literature. You can have a read on net. So for example, you have a bisector method. So you can draw a vertical line so that you're dividing the falsified output area into two equal areas. You have mean or maximum here. So if you have a plateau here, you just can take the mean of this value and this value here. And then you can take smallest or maximum, largest or maximum. So all these are possible. So if you just go back here, so in largest or maximum, you can take this output. You just end here. Smallest or maximum, just output here. Yeah. All these have been tried in literature because of fuzziness of the type of problem you are trying to solve here. But still, the central method is logically, obviously, the most representative of expected output. Yep. Now, how do you go about applying the approximate method using the specified output? If we just look at the next slide here, so this is what we have now. We have to choose an interval. Yeah, definitely we won't take below 25 because all outputs are 0 here. We're taking sum of products. We're taking sum of products of X with membership functions. You would want to choose values which are non-zero. Okay, so in this case, you start at 25 and you start at 100. So we can take regular intervals. We won't take a 0. The 25 itself, the membership of 0, so it won't compute anything to the output. So we could start at 30, for example, and then take 30, then 40, 50, 60 at regular intervals. Now, of course, when you do that, if you choose 30, for example, you would have to know what value is taking here. And if you're choosing, then it's clear if you're able to find the transition here. Yep. If we found, what I did simply here is find the equation of this line here. So this is what's given here. And then you find at what value does it go to 0.4, because this is the transition, if you want, from being a linearly rising one and then staying flat at 0.4. Same comment here as it's going down. You have a certain point here where it is actually going linearly down and then staying fixed at point. So it's important to find these points. So if you find the equation of this line and you replace by 0.4, I got 35. Then you find the equation of this line, which is y is equal to 75 minus x over 25. Very simple. Just find the equation of this line and then plug in 0.4 again. I got 65. The next important transition when this function actually becomes 0.2. So I've got 70. So once you've got these important points here, if I choose 30, for example, I can work out this membership. And 40 definitely is after 35. So we can choose 0.4 at 50, 0.4, 60, 0.4. Then when you choose 70, you have to find this value from the equation of this line. Yep. And then, of course, when you choose 80, 90 here is going to be 0.2. So when you do that, these are the points you get. So 30 is 0.2, just on the rising edge. 40, 50, 60 is flat. At 70, it is falling down, but it is 0.2. When you plug in the equation, 80 is also 0.2, 90 is also 0.2. Yeah. So once you get this, you just have the product of X with its membership value. This is what you've done here. I've already factorized it, so you can see all the values of X which have membership value 0.2, so 30, 70, 80, and 90 have been grouped together, and then those having membership values of 0.4, so 40, 50, and 60 have been grouped together. So basically, you could have written, of course, each term individually, 30 times 0.2 plus 40 times 0.4, and so on. I've done it directly, and then you would divide here, of course, by the membership, by the sum of memberships. So you have 0.4 3 times, 1, 2, 3. And then you have 0.2 4 times, and you have this one. So as you can clearly see here, this is why we are not choosing value membership value 0, because it won't contribute anything in the numerator nor the denominator. So it's useful to improve them. If you do that, we get a value of 57% as the crisp value for the output you will now feed. You can see clearly if you relate back to this one we said right at the start, if you get a value above 50 here means you have to do cooling. So 57% saying yes, you could be doing some level of cooling, but not a lot. It's up to you to make sense what this 57% means. So in this problem here, you're going to feed 57% to your air conditioner controller and you take appropriate action. Now I ask you to work out the situations for the following. So your target temperature will be 21 degrees Celsius, and what if your room temperature was 31 or 15 degrees Celsius. So do work on these and email me if you are facing any difficulty. I'll be doing a video on that when we discuss the drill sheets, so we could have a discussion on that. Now, I'm also going to send you example number 2 in a PDF document, which relates to a scenario where the level of risk of funding of projects to be assessed. So it could be typically in a bank, assessing the request for loan, for example, from a company. And here our inputs will be the extent of staffing and the percentage of funding already available and the extra funding will go to the bank. So I'm going to send this PDF and then do a small video as well, like I'm doing now, to sort of discuss again this example. So I'm going to stop here right now, and please wait for my next video. Thank you.